Students, yesterday I was discussing about the instrumentation part of the NMR. So this is how actually the NMR spectroscopic unit is going to look like. So I told you like it's going to be usually since the NMR spectroscopy, whenever they are going to go for measuring the absorption patterns and measuring the resonance. So here they are going to apply the magnetic field in all 360-degree directions. So that's why usually the magnet, the external field, external magnet is going to be usually circular, and will be dome shaped like structure. So this is how the whole instrumentation part is going to be. And if you come to the limitations, as I told you already, limitation is like only in case measurement will become little difficult. For only in few cases where the isotopes are the nucleus which we want to measure, if they are very less naturally occurring, then the measurement of such kind of nuclei will be means resonance for such kind of nuclei measurement is going to be little difficult. That is, for example, like C13, if you are going to think of, it's 11%, whereas if anybody want to go for O17 NMR, again it's going to be difficult, because any of the naturally occurring molecule if you take, because the one which we are going to be studying, usually they are naturally occurring molecules, and all these naturally occurring molecules will have very low percentage of O17 atom, so which is 0.035%, which is very less. So therefore if you want to go for O17 NMR, we may not able to get proper results, because a resonance is not going to be observed in all the molecules. In results are not going to be complete, which will not give us any kind of correct analysis of the particular molecular aspects. So this is the very important limitations of NMR, whereas NMR we can do with the solid samples, liquid samples and all those things, and I told you. So whenever we go for liquid samples, means whenever we want to do the NMR for the solubilized dissolved samples, because particularly in case of biological macromolecules, in the solid state whatever we are going to study, which cannot be completely correlated or extrapolated into the natural environment of the cell, because inside the cell all these molecules are going to be continuously interacting with the water molecule or the solvent molecule. So therefore it is always necessary to study the structure of these different biological molecules in a natural state, that is in the dissolved state, but we can do analysis even at the solid states also. And NMR is one of the method which actually gives more structural informations next to X-ray diffraction studies. X-ray is the ultimate method which will give you the very detailed and very good analysis, but only thing is it's a destructive method, whereas NMR is not going to be so it's not a destructive method. Whatever the sample used for analysis can be further used for other kind of analysis or studies of the sample. So that's a one. And I was talking about this Fourier transformation methods also. Fourier transformation method is a very important method which actually give lot of advantages to the NMR spectroscopy. So in a conventional NMR spectroscopy, electromagnetic radiation is supplied to the source as a continuously changing frequency over a pre-selected spectral range, whereas in case of with the advent of the Fourier transformation method, and time domain can be resolved into frequency domains, and we can now continuously alter the alter the frequencies, and as well as we can also measure the NMR spectroscopy at different angles, as well as we can able to correlate those particular results and find it. For example, you can see with a Fourier transformation what is the benefit. So earlier we used to measure amplitude and the time versus time in seconds as a signal, we used to get the graph, but now because of the advent of Fourier transformation, we can convert it into amplitude versus frequency which will give now earlier which was giving 4-5 peaks, now it can be converted into one single peak and will give you a lot of information about that particular molecule in one single peak. We can get it. So that's the advantage of Fourier transformation. This Fourier transformation is a higher mathematical calculations through which continuous data which is going to be obtained by the analysis, okay, through the instrumentation is going to be analyzed, and it will be superimposed and it will be converted into a single image or data, we can say. The next types of NMRs are two-dimensional NMRs. Whatever I explained you till now, all these factors are going to be used in one-dimensional NMR. So two-dimensional NMR means, so here if you are going to see in the NMR, you can either measure, you can concentrate on chemical shift, or you can concentrate on spin splitting or J constants, or you can concentrate on FT. So like this, one component, or even you can concentrate on nuclear overhauser effect, like this. But in case of two-dimensional NMR, so here what people are going to do is, instead of concentrating or instead of pushing for only one particular principle, they are going to use more than one principle at a time in a same sample at a same time, and they are going to measure the behavior of that particular molecule with respect to different principles of NMR. Like for example, one way you can measure chemical shift, another way you can measure the interaction like nuclear overhauser effect. Okay. On the other hand, people also go for measuring the FT, how exactly the behavior molecule will change when the frequency is given parallelly, perpendicularly, like that they are going to study. So this is what the two-dimensional or multi-dimensional NMR spectroscopy is, which is going to give more information, and it will be having a lot of advantages where one-dimensional NMR. So generally in one-dimensional NMR, we are going to have only preparation, evolution and detection phases, or preparation phases again. But whereas in two-dimensional NMR, we are going to come across with preparation, evolution, mixing time, and then detection time is going to be there. So here T1 means it is the time between the first pulse and the signal detection, and T2 means it is the detection time. So like that. So these are the different aspects, like preparation time, spin system relaxes and then excited by the RF, and evolution time T1 means it is the chemical shift and spin coupling evolve. This is the time domain which is incremented during the two-dimensional experimentations. So generally what will happen is that nucleus which is going to be involved in spinning, okay, so now it is going to get affected under different factors, and each coherence evolves at its own characteristic frequency of function of the chemical shift, and the scalar coupling corresponds to the nucleus. So then we can go to the mixing time. Mixing time is nothing but it is made up of pulse sequences which achieve coherence transfers in such a way that the different frequencies can be correlated, because in two-dimensional NMR we are going to correlate the whatever the signals which are coming out of the studies together, and we are going to measure the correlations there. So detection time, it's observable transverse magnetization which is recorded, and usually it is labeled as T2. So there is different type of two-dimensional NMR. 2D FTM NMR is there, noisy is there, COSY is there, rosy is there, okay, like that. Different type of two-dimensional NMR spectroscopies are available. In FT-NMR, two-dimensional FT-NMR, people are going to measure. So here instead of one dimension NMR, so depending on the size of our molecule, so different variations and combinations of two-dimensional or multi-dimensional NMR is going to be utilized. So here people are going to go for additional dimension is going to be added up here by varying the length of time, and as well as the system is allowed to evolve following the first pulse and resulting the outgoing signal, the f, which is then Fourier transformed and gives the spectrum. Then we come across with COSY, that is correlation spectroscopy. The correlation spectroscopy, that is again two-dimensional NMR spectroscopy, it is 2D COSY. So here pulse sequences are going to be like this. There will be first 90-degree pulse will be there, followed by again 90-degree. The first pulse is going to be given. The resulting oscillation magnetization is then acquired during the T2, that is in the detection time. Then another one is noisy, that is nuclear Overhauser effect correlation spectroscopy. So in the noisy, the interference of electron makes this coupling undetectable generally whenever the electrons are going to get interacted with each other in NMR spectroscopy. But with the noisy, so here what people do is they decoupled the electrons and neutralize them, the bond coupling through electrons, allowing the space coupling of the nuclear Overhauser NOE, that is nuclear Overhauser effect, to be detected. So that is what they do here. First they give pulse at 90, then followed by again pulse at 90 and again pulse at 90. So because of this, what will happen is that the T1 is going to get increased into number of times and we get the signals at T2. So this is how actually usually the two-dimensional NMRs are going to look like. So you can see one-dimensional NMR at one side and the other is on the other side. We are always plot will be by using chemical shift we are going to do it. So this is again you can see with the frequency, the Lamar frequency of B and A, how it actually situates, and this is again the three-dimensional graph of chemical shift of 2D NMRs. If you come to the applications of NMR, it is used in molecular structural determination, one of the very best method which I already mentioned to you people. So the NMR spectroscopy is a main method for structural determination of organic compounds. It's a particularly used for both the low and high molecular weight molecules. Structural and dynamic informations are going to be obtained from the NMR spectroscopy, mainly because see here what happens is that chemical shift is going to be plays very important role in the structural studies, as the NMR signals are going to get vary based on the chemical shift, and chemical shift is going to happen due to the interaction of two different nuclei, and this interaction is going to be again guided by the distance at which these particular nuclei are going to be present. So which will give lot of inputs regarding the protein or the biological molecules like protein, nucleic acids, and interaction between the in case of enzyme study, like interaction between the enzyme, substrate, active site, all this can be analyzed by using the NMR spectroscopies. And strongest spectra are obtained with the liquid samples actually compared to the solid samples. The technique is closely related to the people are actually the MRI. You might have already come across with in clinical diagnosis. People use the magnetic resonance imaging. Magnetic resonance imaging is the superimposed NMR spectroscopies. A large number of spectrals are going to be get superimposed and converted into an image. So again through the FTs they are going to do it. So this MRI is being widely used in clinical diagnosis. So because all of us know one or the other time we might have gone through it because of the clinical issues. Another kind of applications is people are using this NMR spectroscopy in the study of protein folding, ligand binding, protein interactions, molecular mobilities within the proteins, that is within the protein there will be structural dynamics are going to be there, because protein structure is dynamic. Inside the protein the core amino acids are going to show sometimes small movements which is involved in the conformational changes. So all these studies are being done with the NMR spectroscopy. Even people are actually measuring how exactly the behavior of the proteins are going to get altered with the change in pH, temperatures, particularly pH. And even we can able to study the because there are different types of NMR, like P31 NMR we can use to study the effect of phosphorylation or phosphate group, or the addition and deletion of the phosphate group into a particular molecules like phospholipids, or even in signal transduction where phosphorylation and dephosphorylation plays a very important role. So all these kind of studies can be done by using NMR. Interactions of molecules, as I told you, can be studied by chemical shift. So this is all about the NMR spectroscopy. So thank you, and further, in case if you have any doubts, please do feel free to contact. There's a lot of information available, and it's a very important method. Concentrate on this particular method. There are a number of calculations solving the spectra. If number of lines are given, chemical shift is given, number of carbons are known, you can actually find the structure of the molecules like that. So many kind of problem solving is there. So if time permits, I'll make some videos on this aspect of solving the problems, or identifying the spectra, or from the spectra to write the structure of the molecule. Okay, so thank you, all the best.